Oh, wait, it's supposed to be here though.
I did mine at home.
Or red.
Okay, I got it right.
Or you could just put IR red.
Marissa, can I ask a really kind of stupid question before we get started? So orbitals only have 2 electrons in them, right?
Yeah, like each little suborbital.
And then, so a suborbital is part of the larger shell. Is that?
Yeah.
Okay. So I think in my mind, they were all kind of following on, like, hanging out in the same plane. And then I was reading the text this morning and was like, oh, that is not what's going on at all, right? I'm sure you said this on Tuesday, but it just flipped
Yeah.
in my mind. So, like, the pairs of electrons are each in their own suborbitals, and then each, like, the aggregate suborbitals make up the shell.
Yeah. So it gets really complex. I think we're gonna do a modeling lab too later in the quarter, and you'll see like the orbitals. And I think that would help. Yeah. But that's basically what's happening is like, okay, this is a 1s and there's 2 electrons like floating around in here somewhere by the probability density map, right? We can't say where, we just say there's the high probability here, low probability as we go out. And then, yeah, with the 3 P's, so 2 electrons on the here, 2 electrons in there, 2 electrons in somewhere in there, probability. And then, yeah, so 2 electrons can occupy this space. 2 electrons, or at least that's what 2 electrons, 2 electrons, 2 electrons.
How did they figure out the one with the donut?
It's all math, ultimately.
Really?
Yeah. It's kind of beyond my comprehension.
Obviously that is what I wondered when I looked at that picture. Not any of the other relevant things that I should know, but like, how did they figure that out?
All right, so just a few reminders. So of course, midterm next week, so we'll review Tuesday and take the midterm Thursday. And so again, just email me a reminder if you need to take the midterm at another time, so we can do that through the testing center. Otherwise, we will do it Thursday. And so if you missed class on Tuesday, definitely check out the video. So you'll want to look at that. And then I'll be posting the study guide today, so that should go up today. If I don't have it up today, you can always email me and be like, hey, post that study guide. But no, I'm going to try to post it between now and lab, so you can yell at me at lab too. And that will be up. But really, that just covers the topic, so I don't think it's too useful, but I would just review your quizzes as well, review all your math, review the homework, and know all the concepts. Any questions about anything from yesterday before we kind of move on to the rest of the chapter?
Oh, can you go over the Schrodinger equation?
I guess what? Because I guess all we need for our class is like we just appreciate it, so we're not doing anything with it. Because, you know, like we were saying, it can only be solved for the hydrogen atom, and that gets nasty really quickly. Because there's all these like operator math things that are kind of beyond this class. And so it doesn't really help us. We just kind of appreciate, though, the pretty pictures. So that's all we need to take away is once you start plugging this in, and, you know, again, I don't want to go into the math of like what this is expanded and all that, but they put that into computational chemistry. So computational chemistry started super early in the 1920s because they had this problem of they couldn't solve the Schrodinger equation. So that's where computational chemistry came along to at least give us closer and closer approximations, and then we get the pretty pictures. At least that's where we're at, is we got these pictures from these equations, and this is what all the orbitals look like. And that's what we were saying with like the wave function squared then with Schrodinger's equation. So all that is giving us is the pretty picture. But yeah, all this is done computationally now. Computers are much better at math than we are. Other questions? So now let's look at what we mean by excited states. If you had lab already, maybe you figured it out. And so we want to write the electron configurations for excited states, or be able to recognize when it's in an excited state. And so we can examine lithium. So we'll just look at lithium in its ground state. And what's the electron configuration for lithium in the ground state? Right, 1s, 2, because you got to fill up all 2, 2s, 1. So that's our ground state, or we usually just say, right, our normal electron configuration. And so that's what's drawn here, represented by the little line notation. So of course, 1s being the lowest, and then the 2s is next. And so now if we say, well, you know, what is lithium then in the, well, in this case they said first excited state. So first excited state just means you're promoting it to the next energy level up. And so in that case, it would be any one of the 2p's. It kind of bothers me that they only drew out one 2p. So you have 3 degenerate 2p's. We don't know which one it jumped into. And they would all be the same. We draw that, and we can draw our transition. So promoting it to the next energy level. And again, it could be any of these, because don't forget the term degenerate, which means same energy level. So just from this information, we don't know what p orbital it went into, px, py, pz formally, but just one of those. And then, of course, we can write our new electron configuration. I'll just stick it in the first one. And so now what's our excited state electron configuration? Well, which one do we promote, though?
2s. So it's 1s2, and then it would be 2p1?
Yeah, so 2p1. And so what are other possible options? I think people are kind of naming them, so we'll just list this as other excited states. Oh, sorry. So 1s1, 2s, well then it would be 2s. So you're starting from here. So you're saying promote one of these. So then where could we promote it? Sorry? Oh, I mean, so we could pick. So we don't know. So right now we don't have enough information. So we're just kind of assuming, well, what might happen? So we could promote it to the 2s. Maybe we go to the 2p. Like, we're not really sure. We're just kind of listing these possibilities. So what do you want to do for the first one? 1s1, 2s, 2. And the important part, and we can tell that this is lithium just in an excited state, is we're just totaling up the number of electrons. So 1 plus 2. So that gives us 3 total. So we can tell, okay, this was lithium. It's just in some sort of excited state.
Could you also do 1s1, 2s1, 2p1?
So that could be another possibility. And so the next thing, and so we don't have the equations for this, and this is like beyond the scope of this course, but you would have to see, like, are these allowed transitions? Like, what wavelength would it correspond to? So then that tells us if it can actually happen or not. You could also, so what if we promoted it to an even higher level? So other possibilities. Maybe looking at this outermost one. So the only thing with that one, because then you're promoting like 2 electrons. So then I think that's kind of a bit too much, because you usually just do like 1 at a time from one transition. And it's probably the outermost, but that being said, I think they could still happen. But what's higher than the 2p though? So 3s, that's before. So you could promote, what if you had, a higher energy? So instead of going from the 1s, or excuse me, from the 2s to the 2p, they could have gone from the 2s to the 3s. So then that would give us, I'll try to color code, I should have done a better job. So then that would give us 1s2, 3p1 for an excited state. So would have to calculate wavelength to see if allowed. So again, that would be beyond the scope of this course, but if you took probably like CHEM or inorganic chemistry, you might have to do this where you would actually be calculating if those would be allowed transitions or not. So can you actually give it the appropriate energy to make that transition? And then there's other rules for whether it's allowed or not based off of like spin states. All right, so for this one, take a minute or two with your neighbor, your friend. So write some possible configurations for hydrogen for the excited state.
Oh, the different ones. I'm so sorry. Yes, yes. I get you now. I was like, wait a minute. But yes, no, I totally understand.
see, so do we have some possibilities? So 2s1, 2p1, so 3s1, yeah, we don't know. It just depends on if that frequency is correct, then yeah, it'll be promoted. Other possibilities? I mean, really, it could go crazy. 22. 22s1. I mean, it exists theoretically, right? You get closer and closer and closer to infinity. So it's just about if it's at that right frequency. And so, yeah, you could go crazy, 3d1, as long as it just has one electron total. So we know, oh, yeah, that's hydrogen in a really excited state. Yeah, in reality, that's what I was trying to find out, but I think so probably not, just at least for hydrogen. So that's where like the spectral lines come into play. So you'd have to dig into more research and see if people have figured out like, yeah, this line corresponds to this transition. So that's what's going on. So with hydrogen, you only have 6 lines. So they know those, right? So those correspond just to I think the S transitions, so the main transitions. But yeah, and then obviously that's why, and if you have lab this afternoon, you'll see the tubes and the lines and what we're talking about. But that's why, of course, the heavier elements have more complex structures since there's more transitions. Let me see if I can find it so everyone knows what I'm talking about. Yeah, so there's this graph in lab. And so, of course, this is kind of hard to see because I can only zoom in so much. But you get the picture that hydrogen, so it's simple, right? It only has one electron, and so it only has so many allowed transitions in the visible region. And so there could be more transitions. And then what we'll do later is you'll see that like organic molecules, so organic compounds are always white usually. But why they're white is just all their transitions are in the UV region. And so if you shine a UV light on organic compounds, so we use a TLC plate to put them on there, then you shine a light on this TLC plate, and they glow. So then you can see where your compounds are, and that's really cool. And that's how people know how to separate them. And so we'll talk about chromatography later, but that's what's going on there. So with all these compounds, right, obviously as we go down the periodic table, if I could find a better version, it's not as blurry. Oh no, it's the same link. No, why is this so tiny? That doesn't help me. Yeah, but you can tell, so, right, all these elements, especially with a lot of electrons and all of, like, the d orbitals, the f block, like, all of them get so crazy, right? There's so many lines, all because there's so many allowed transitions, all those electrons being excited, and so they get really complex. But yeah, you'd have to dive deeper into the research to see what people have found, if they've correlated them to the exact transitions or not. Get really bored. Just making sure I didn't. Oh, let's look at this again, and we'll just point out some things again. So looking at just funny electron configurations, kind of why they are. So for instance, we can look at copper. And so on an exam, I would not expect you to necessarily know this, so we would just fill it up normally. So 4s2, 3d9, at least that's what we would expect. But they've given you that really it's this, so 4s1, 3d10, and so you can tell kind of why that is. You write out your orbitals. So we remember the 4s is really close in energy to the 3d. 1, 2, 3, 4, 5. And so let's first draw kind of what we would expect. So copper, 11 electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So that leaves 1 unpaired in the D. And so for some reason, electronically, mathematically, it's more favorable to actually break this interaction and promote 1 in the D. And I think it's a geometry argument. And so what you find, like this is more reflective of the geometry in nature. So they tend to take square, planar configurations. And so that would put these D orbitals into a different orientation and change the energy of the 4s. And so that's why, yeah, so then it'd be 4s1. I just wanted to and all the D orbitals are filled up instead. And this is probably pushed lower. And let's just add. So we'll revisit this kind of later in the course, but we find, like for example, if they're going to take a square planar configuration, then their D orbitals actually change to something like that. And so that probably changes our energy level. I'm not sure where the 4s, so I'd have to draw, we'd have to be looking at something more real than this, but probably the 4s is higher somewhere. And some of these D's have dropped lower, which makes it favorable to have that. Since you always want to fill up with the lowest energy, and so that's really all that's going on with these electron configurations is your compound will take the most thermodynamically favorable geometry based upon whatever it does to the splitting of these D orbitals. So like I said, we'll revisit this much later in the course when we look at inorganic compounds in more depth, but that gives you kind of a glimpse of why they're not predictable. And so again, we have some oddities here. So niobium and molybdenum, so they both only have 1 in the 5s. And again, on an exam, I would not expect you to know that. If you knew it or thought it might happen, I would also accept that electron configuration, so both would be correct. So again, I just care about the total number of electrons. And so same thing with down here. So we mentioned Just a reminder, so lanthanum and actinum should really be here, especially because this is 15 across, so that doesn't match with our F. But if you put the lanthanum as 4F1, I probably wouldn't mark you wrong. Again, just have the correct total number of electrons. Don't forget about them. And so cerium makes sense with what we expect, but sodium gets funny. And that's just difficult to predict. And then, are we comfortable with giving like ion electron configuration, like sulfur 2 minus? What's the electron configuration? Should we practice that? Let's do a couple. Let's start off, we'll do sulfur 2 minus. And then when you're done with that, try, let's do palladium 2 plus. Do we have sulfur 2 minus? Yep. could also do the abbreviated form, so neon, and 3s2, 3p6, same thing. Do we have palladium? What's palladium?
Krypton,
4d6. I think that's correct. Can't count. Where's a periodic table? So palladium, so 1, 2, 3, 4, 5, 6. Yep, perfect for 2 plus.
I have a question really quick. Like if we were to do boron, like plus 3 or something, how would you do that? Because it's like the first of that whole thing.
So then boron 3 plus. So that would bring it all the way back to just 1s2.
1s2. Okay.
I'll write that somewhere. Boron plus 1s2. Oh, 3 plus, sorry. So yeah, you just take off, you know, the first 3 in line.
Okay. Thank you.
And I mean, you could get really crazy too, like, you know, now we could say write a possible electron configuration for boron 3 plus in the excited state. So now what would that look like? So what are some possibilities then? So 2s2, my only criticism is we have like 2 in the excited state, but we could still do that. But usually you just want to do like 1 at a time. So this would be 2 E's are excited. So what would be other possibilities?
One is one, two P one.
So 1s1, 2p1. So I like that better since we're just promoting one of those electrons to a higher energy level. What other possibilities?
One S1,
1s1, 2s1, and any others? We could go crazy, 1s1, 3d1.
So if you had those electron configurations, so if you gave us just 1s1 and 3d1 and said, what element is this? What would tell us it was boron 3 plus and not something else?
So what the question would have to say is element, and you may actually have a question like this. So. Oh no, it's just funny. So right, element X has a 3 plus charge and an excited electron configuration of, so we'll just do 1s1, 2p1, and so then you could say which element. And so from there, right, you have to start, well, okay, working backwards. I have 2 electrons, but then if it has a 3 plus charge, now I know I need to add 3 more to that to get back to the neutral. So now I'm at 5 total electrons on the neutral, and then so you get back to boron. So yeah, you could definitely see this type of question on your exam. Let's finish up the tail end of this chapter. So the last bit of the chapter is just talking about the atomic radii trend. And so let's look at the overall picture first, and we'll look at the details. So the smallest radius is going to be fluorine, and of course hydrogen, helium, but just looking at the main one, so fluorine is going to be really small. And so again, what you're thinking about, why that is we're just filling in more electrons on that 2p as we go across. So comparing, let's just compare, boron in pink, so it has 1, 2, 3 electrons versus fluorine. So fluorine would have 1, 2, 3, 4, 5, 6, 7. So we're filling up that p shell, getting closer and closer, or rather neon would be the smallest, as we fill in all the electrons on the 2p. And so they're not at a further distance away, so again, the effective nuclear charge is stronger, so it brings those electrons in a little bit tighter, and so giving us a small radius. And so we can look at this trend as well. So lithium to beryllium. So beryllium gets smaller as we fill up the 2s, right? So this is 2s1, then 2s2. So now, right, the 2s2, this second electron, still the same distance away, so it's still in that same s orbital, but now since there's 2 electrons, again, stronger effective nuclear charge. And then, so you can see, let's zoom in. So now boron, it has more electrons. They're still in the 2, so our overall 2 energy level, but we did add a p to it, so it's about the same radius, so 2s2, 2p1 for boron. So added an onion ring essentially. But then we can see then the rest go down, smaller radius, as we fill in the entire 2p. So 2p5. And so that trend generally follows. So sodium, magnesium, aluminum still has a smaller radius. And then, of course, the transition metal elements, we mentioned that things, again, get funny. Those d orbitals aren't actually degenerate, so they start taking different configurations. So the radius is about the same and doesn't really follow the trend that well. And then we pick back up with the p block over here. Then obviously as you go down the periodic table, we're adding more physical shells, so of course their radius is increasing, so francium would have a very large radius. And then, so we mentioned too that cations are always smaller. And that's just because, right, again, you have your protons in the center, electrons on the outside. So if you have less electrons to hold in, then it can hold them tighter, smaller radius, or maybe you're even losing, right, your outermost shells. So like we've seen with sodium. So sodium has our 3s1 for the valence. And of course, sodium plus, we lose that. Let me write the electron configuration better. So argon, 3s1. Versus sodium plus, right? So we lose our 3s1 entirely, so that's going to have a small radius. And then that, of course, means that your anions are always large. And so opposite effect. So if you're comparing, let's go back to sulfur. And sulfur 2 minus. So sulfur, we said it was neon, 3s2, 3p4 for the neutral, then neon, 3s2, 3p6 for the -2 species. And so it still has the same number of protons in each one. And so now the electrons outweigh the protons. They can't hold them in as tightly. And so that radius is getting larger and more diffuse. So it has a larger radius. Yes?
So does that mean that things with larger radiuses have smaller ionization energies?
Yes. So we saw that with our ionization energy trends, right? The ionization energy was decreasing as we went down. So exactly, they get more diffuse, so then they're easier to pluck off. And then with the same oddities that you see the ionization energy, and we can kind of see that in the radius. So yeah, everything should kind of really be reinforcing each other with all these orbitals. All right, let's try some practice problems. So I'll give everyone a couple of minutes to get started. So what is the uncertainty in the velocity of an electron whose position is known to within 2 × 10⁻⁸ meters if the electron is moving at a speed of 5 × 10⁵ meters per second? So what fraction of this speed does the uncertainty represent? see, so let's start walking me through this. So what formula do we need? Oh, say it one more time, sorry. And then,
You asked what equation.
yeah, so what, give it to me.
Oh, okay. The uncertainty of x times.
Oh, sorry, let me rewrite.
Times the uncertainty of the velocity. And then it's the greater than symbol.
And is there like a mass factor in there too?
Yeah, I said,
Oh, I missed that.
and then h divided by 4 pi.
So there's our formula. And so they didn't quite give us all the information we need. And so what might we need to look up?
The mass of an electron.
So mass of an electron, does anyone remember it?
Oh, 9 times 10 to the negative 3 kilograms. Negative 31.
Oh, sorry.
So 9.109 you said?
Yes.
9.109 times 10 to the negative 31
Kilograms.
kilograms. And so that's excellent, so we're in kilograms. And so now what do we need to do? So plug in what we know. So it says whose position is known to within 2 times 10 to the negative 8 meters. So we're trying to figure out uncertainty and velocity. We have that. We have the mass now. So it looks like we can start plugging everything in. So 2 times 10 to the negative 8. And this is in meters, so that's good. So we're trying to find, so we have our mass. Trying to find our uncertainty and velocity. Oh, and then what's Planck's constant again?
6.626 times 10 to the negative 34. What is the speed then? Like,
So,
how does that play in, or it doesn't matter?
so it's for the second half. So we're first going to find the uncertainty and the velocity. And then it's saying, well, if the electron has this total speed, though, what fraction of the speeds then? So then we're going to see how accurately can we really even experimentally determine this speed.
Okay.
So that's what this is telling us. It's like basically we took a measurement in lab, we got this 5 times 10 to the negative 5th, but by this rule, we can only figure it out so accurately, so how bad is our measurement? And so now let me bust out the calculator. So I'm just going to plug for this constant first. Where's my pi symbol there? And so I'm going to solve for velocities once I get this number, and I'll just divide by my meters. I'll write it out. So delta V is equal to, so calculator spat out this number. So 5.27 times 10 to the negative 35, then divide by, I'll just plug in delta X and mass. And you could have multiplied them first, I just divided them one by one. Oops. So do we all get this answer? So about 2,894 meters per second is our uncertainty. And let's see. Actually, we only had one sig fig, so we can only report to one sig fig, so 3,000 meters per second. And so it says, what's the fraction of this then? If this is what we measured for the speed, this is our uncertainty of our measurement. How bad is our measurement? So take our number. So if we want to do the rounding, so 3,000 divided by 5 times 10 to the 5th. Convert that to a percentage. So 0.6%. And so that was, again, just 3,000 meters per second divided by what it said our speed was, so 5 times 10 to the 5th. So, I mean, decent accuracy, but obviously there's, you know, some error. And that's just how quantum mechanics is. That goes back to every time you try to measure it, you perturb it. So it's extremely difficult to study this. All right, let's try another type of problem. And so again, take a few minutes to look at this. And now all it says is, so which of the following sets of quantum numbers are allowed for an electron in an atom? So let's look at this one. So what do we think about this first line? Allowed, not allowed? So I see some nods. Allowed. Do we want to, where might this be found? So what atom might it be? Take it a step further. What does the L tell us again? P orbital, so we know it's a P. We know it's on our second energy level, so what might one example be? So it could be boron, I think I heard carbon, nitrogen, so any of those. So we don't know which one, could be any of these, we don't have enough information. Excellent. What about line number 2 now? So 3, 0, plus 1, negative 1/2. Is this allowed or not allowed? So not allowed. So what's wrong with it? So this, what does the 0 refer to again? A P or an S? And so mathematically, we can already tell it's not allowed, so negative L to positive L. Or, you know, again, you can kind of look, well, this is an S orbital. There's only one option. That should be 0, so that doesn't make sense. So you could correct it to make it right. Or you could increase the L, since, you know, P is allowed on the N3 energy levels. So we could change this to a P, we could change this to a D, and then it would be allowed. Line number 3 here. So 3, 2, -2, -1/2. So yes, everyone's in agreement. And so what does the 2 stand for again? A D. So it's allowed. And then take a glance at your periodic table. So who might this be? So anyone from, so any of them from scandium to zinc, I like it. So we don't know, just somewhere it's on the 3rd energy level in the D shell. Any one of those are a possibility. All right, our next line, so 1, 1, 0, 1/2. So allowed, not allowed. Not allowed, so what's wrong with it? So I'll just write L has to be N-1. So if something is wrong, we could change our N to literally anything else, or change the L to a 0. So not allowed. Then the last one, so 2, 1, 0, 0. Not allowed, so what's wrong with it? So +1/2 or -1/2. Awesome. So any questions on this? So this would be like a good multiple choice question on an exam, you know, which one of these is allowed, which one is not allowed, something like that. So let's do some practice. So see if you can practice with the arrow notation, and I'll leave it up to you, because your book, again, likes to do this sideways thing, which, you know, is fine. We should be able to interpret that, but my style, I always like to go up and down since it reflects our energy levels. But just either way, practice writing your arrow notation for nitrogen, magnesium, sulfur, and neon. I'll try to go over them. And so obviously be comfortable with reading either horizontal or vertical configuration. let's do nitrogen. And so did somebody give me at least the electron configuration?
Two S2, or I'm sorry, 1S2, 2S2, and 2P3.
And so just translating that, it should have looked something like that for your arrow notation. And of course, there should only be one arrow in each of the P's since they're degenerate. And again, this reflects its reactivity. And we could say that it has 3 unpaired electrons. And of course, we said because it has 3 unpaired electrons, it likes to make 3 bonds, or at least it tends to. And of course, we have those 2 electrons in the 2s, and those can also do action, as we've seen. So now let's look at magnesium. And so what's its electron configuration? One S2, 2P, 2P6, and then 3S2. So now if we want to write this whole thing out, so we'll start, should technically start bottom up, but for the sake of my paper space, I'll try to put the 3S and the 2P close together. 2S, and then 1S is further down. Filling up all our electrons. And of course, usually you just see the 3S represented. These are the core electrons. Let's do sulfur. So give me the electron configuration again, please. You can give it to me abbreviated. Neon, 3S2, 3P4. And so it kind of gets cumbersome to write all the other ones down there. So let's just write, so 3P, 3S, those are the ones we care about. Obviously, all the cores are going to be filled in. So starting in 1, 2, 3, 4. And so, of course, sulfur has 2 unpaired electrons. That's when we know it likes to make those 2 bonds then, for the most part. Any questions on this? What's the last one? So neon. So what's the electron configuration for neon?
1S2, 2S2, 2P6.
So excellent, and then we just want to draw that out. So 2P, 2S, I'll just throw in the 1S. Of course, noble gas configuration. So all of them build up. Oh, sorry. And then before I forget, so this came up in the homework, and it comes up in lab too. But it'll ask questions like, how many orbitals are in, let's just say, the third energy level? And so all that's saying is all the allowed ones. So if you're on the third energy level, right, you can have an S, a P, and a D, which means there's one S, 3 Ps, and 5 Ds. So that gives you 1, 2, 3, 4, 5, 6, 7, 8, 9 total ones. But then there's also a formula. So this just corresponds to how many orbitals. So that would be n squared. So you're in the third energy level, so 3 squared gives you 9. So that works out for all of them. And so that means total electrons in an energy level, that's just going to be 2n squared. So that makes sense, right? Each one of these little orbitals holds 2 electrons. So just multiply that by 2. We know it's 18 total. And of course that works. So first energy level, and squared just gets us back to 1. That makes sense. We just have an S. Second, n squared is 4. And again, S and P are allowed. And so forth and so forth. And of course, this just gets tricky if you're asked about, some sort of theoretical energy level. So we can ask, so how many orbitals and how many electrons can the 7th energy level hold? And so you could figure this out. So obviously this would be theoretical, so you'd have to keep kind of going on and on with the pattern, which is where the n squared works out. So there are 49 orbitals then, so 7 squared. And the total electrons, so 2n squared. And so now, can't do mental math, so 98 total electrons. So easy enough to work out in the lower energy levels, but if you ever see anything really high, just resort to the formula. And if anyone ever wants to see how to work that all out, I'm more than happy to go through that. So you just keep going theoretically. So F and G, and so you can kind of see the pattern. You go 1 to 3 to 5 to 7. So then the next G would be 9. So 1, 3, 9 is G. But all that is, again, just theoretical math at that point. But kind of, if you could, so there's, in like the theoretical research area, and like kind of where chemistry can look, because now the question is, well, how can we make more synthetic elements? And so what they find is that you'd want to continue with these patterns mathematically and kind of find the stable areas. So if you could calculate, for the 7th energy level, how many electrons would that have total to fill in that energy level, again, backfilling with all the other ones. But that might be like a stable future element, like out there. So if you filled up, like the G orbital all the way, theoretically, what is that element? And then can it be made? So that's kind of where research is going, is like, where are the stable ones? They're kind of thinking, like, how could we make noble gases, but, in the theoretical realm of the orbitals that we don't normally work with. And so that's kind of what they're finding too, the areas of stability, but again, another area of research to dive into. All right, over time, so let's take a 10-minute break, and then we'll do our quiz, and then probably use the rest of the time to ask questions, or you can run away if you want to. Definitely ask questions. Midterms coming up. Make appointments with me if you need tutoring. And I'm available nights, weekends, whatever. Just set it up prior to so I can arrange my schedule. And I will stop this stream.